Now that we got all the reactions, it's time to actually get into the joints. So I like to solve the problem using a table. So this table will show us what are all the members and what is the force in each member and whether it's tension or compression. And I like to assume that tension is positive and compression is negative. In order for this to work, I need to assume every new force as a tension force. But remember, when you move from one joint to another, you need to account for the correct direction of the force. So I'll show you in a second. Let's do a quick check. What are the forces here, or what are the members in this truss? Let's start with E. There is member EB. So member EB. There is member ED. Member ED. Member BA. There is member BA. Member BD. Member BD. There is member DA. There's member D. There's also member DC. So for each member, I want to know what's the force and whether it's tension or compression. So let's use the method of the joint. I want to pick a joint and figure out what are the forces in the members connected to it. There is a trick here. First, there is a good joint to start with, and there is a difficult joint to start with. I want you to pick a joint with maximum 2 unknowns. So each member will have one unknown force. There's just like one unknown force here. So pick a joint that has maximum 2 members connected to it. If you chose B, for example, B has 3 members connected to it. That's too much. At each joint, we only have 2 equilibrium equations. So E seems to be a good joint to start with. But right off the bat, because we already analyzed the free body diagram of joint C, I want you to see that the force in CD is actually equal and opposite to the reaction CX. So if you know that CX is going this way, this is the direction of tension. If CD was tension, then it will be pulling on the joint. And that's how you know if the force is tension on the joint. Put your finger at the joint and observe what this force is doing to you. If it's pulling on you, that's the direction of tension. But actually CD equals negative the direction of CX. So because CX is 16, this happened to be 16 kilonewton, and therefore CD is negative. So this assumption is incorrect. It's actually going the opposite way. It's compression. So because I assumed the tension, if the answer was correct, then the force would be tension. Because the answer turned out to be negative, so that means it's opposite. It's going towards my finger. It's going towards the joint, and therefore it's actually compression. So the reaction here, or the force here, is negative 16, and this will leave us with point DC or CD. They are the same. This is the magnitude here is 16. You can put the negative if you want. You don't have to put it, because I will observe what you tell me. Is this force tension or compression? So if you want to say that, yeah, it turned out to be negative because you assumed the force to be tension and the answer was in the opposite direction, and this is compression. Then we figure out the force in member DC or CD. So how do you note the force on the diagram? I want you to consider the force on the joint because CD is compression, so it's going into, there is a force that is 16 kilonewton going into the joint. So if this member is in compression and the force on this end is going into the joint, what's the direction of the force on joint D? Well, it's the same. If it's compression here, it's also going to be compression there. What is the direction of compression? It's going into the joint. So this is the direction of the force CD, and it happens to be also 16 kilonewton. So as long as you take the correct direction of compression, you can use the positive magnitude. You don't have to put the negative here. As a matter of fact, if you put the negative, that means that you're applying a force that is in the opposite direction. So what I like to do is consider the correct direction of the force, whether tension or compression, and use the magnitude. All right, so one problem or one force done, we have the rest to go. So applying the rule that I just said, what would be a good joint to start with? We mentioned that B has too many unknowns. What are the number of unknowns at D? There's 1, 2, 3, 4 members, but we already figured out the force in one of them. So there are only 3 unknowns. Still, that's too much. That leaves us with point E and point A. Both they have just 2 members, so any one of those will be a good start. So let's start with the free body diagram of joint E. So I like to imagine an imaginary scissors, and I will take a dotted line, and I will have to go 360 and include everything around joint E. So I will start here, take a dotted line, keep on going, keep on going. I will consider the external load, and then I will interrupt member BE. So I'm going to take the point E here. So I'm going to say this is point or joint E. I'm going to put the joint here. And the first force was EB. So because I intersected this member, I'm going to replace it with a force in the same direction as member BE. So something like this. Do I assume it going away from E or into E? If it's a new force, in order for tension to be positive, I will assume that the force is tension away from E. So I will put this direction here, and we'll call this force BE or EB. It's pretty much the same. So let's call it force BE. All right. Are we done with the free body diagram? It's still not closed. So you continue the dotted line. You will hit another force, ED or DE. So I will put one force in the same direction of the member, and I will assume it tension as well. So that's the tension. I will call this DE. And don't forget the external load. So the external load was going downward, 3 kilonewton. All right. Is the free body diagram done? Well, if I end where I started, now everything inside the dotted line is in equilibrium. And this is the free body diagram of joint E. So joint E is in equilibrium, meaning that these two conditions apply as well. The summation of forces in X equals 0, and the summation of forces in Y equals 0. So something we've learned, when you find a force with an angle, it's very easy to get the two components of this force. So this will require us to get the angle. What is the angle here? Let's say this is angle theta. So there are a few ways you can do it. You can get the geometry of this triangle. So I'm going to say 0.8 squared and 1.2 squared to get the distance of BE. So if I do 0.9 squared plus 1.2 squared, if I get the square root of this, this is the length of member BE. It's 1.5. This is 1.5 meter. And the reason I did that is because cosine theta is the adjacent divided by the diagonal, which is 1.2 divided by 1.5. You can leave it there if you want. Sine this angle, so sine theta is actually the opposite divided by the diagonal. So that will be the 0.9 divided by 1.5. You can leave it like that. Or if you didn't want to do this step, and that's actually the way I like to do it, you can say that tan this angle is the opposite divided by the adjacent. So I'll do it here. Tan theta equals 0.9. That's the opposite divided by the adjacent, which is 1.2. The problem with tan, it doesn't help us with the sine and cosine, but I can figure this out and get the tan minus negative to the power of -1. So I will get just like tan minus 1, figure out this angle here, which is 0.9 divided by 1.2. I'll get the inverse tan for the answer. This means that theta is 3.687 degrees. So you don't have to do all these steps. You either do the tan and figure out the actual angle and then get the sine and cosine because we will need it here, or you can get the geometry and have the exact numbers. So let's check the cosine. I'm just gonna save this as A, so I'm gonna say cosine A, it's 0.8, so cosine theta, I'm gonna type it here, cosine theta is 0.8, and if you divide 1.2 divided by 1.5, it's actually 0.8. So this is correct. Sine theta, I will just get sine the number I got. It says 0.6. If you divide 0.9 divided by 1.5, it's 0.6. You don't have to waste a lot of time here, but I just wanted to show you that the numbers work and whatever you choose will work with you. So if this is theta, I will get the two components of BE. So what's the direction of the vertical component of BE? It's going upward like this. So I'm going to put it in a dotted line. And if you go away from this angle, it's sine. So this is going to be BE sine theta. And the horizontal component here, this will be BE, because you're going close to the angle, it's cosine. So C is C. Cosine is close. So BE cosine theta. All right. So for this equation here, or for this free body diagram, I want you to note what is the summation of forces in y. You'll realize that it has to equal 0. So from this equation, let's look at what are all the forces in the y direction. You will find there are only 2 forces because the dotted line replace the actual force, so I don't have to consider this force anymore. It's just the vertical component and the 3, and the horizontal component and dE. So BE sine theta is going up, so I'm gonna say that this is the first force, BE sine theta, minus, because the 3 is going down, this is kilonewton. When you add these two, it has to equal 0. And this, when you crunch the numbers, you will realize that BE actually equals 5 kilonewton positive. So this will give us that BE equals 5 kilonewton, and it's positive. So what does it mean that it's positive? That means is my assumption is actually correct. So that means is positive is tension. So this is tension. So I'm going to go right away here in BE or EB. It's both the same. And I'm going to say that the magnitude of force is 5. And the direction is tension. So how did I know that it's tension? Because the magnitude happened to be positive after assuming it to be tension. If you didn't assume the new force to be tension, this rule is not going to work. So just pay attention when you assume a new force to put it in the tension direction. All right, so this is equation 1. Equation 2 is this equation, summation of, well, I did this equation, so equation 2 would be summation of forces in x equals 0. So summation of forces in x equals 0. So what are the forces in x? Well, there is BE cosine theta, so BE cosine theta, and let's assume that this is going against the positive x direction, so it's negative, minus dE is also going negative x, so dE. Is there any other forces in x? Well, actually not. There isn't. So when you add these two forces, it has to equal 0. The good news is we know that BE is actually 5. So it's going in the negative x. We know that cosine theta is 0.8. So when you do the math, I will just quickly do the math. 5 times 0.8 equals 4. And this will leave us with dE equals negative 4 kilonewton. So this will go here, becomes positive, and this will leave this negative. So what does it mean that dE is negative 4? It means it's compression. So I'm gonna go here dE or ED, because the force in both ends, the force here equals the force here, equals the force in any point in the member. There's actually one force in the member. So you can call the member whatever you want. You can call it dE or ED. So dE is negative 4. What's the units? What's the units here? Well, I put it up there. It's kilonewton. So remember to do that. And is ED tension or compression? Because the assumption of tension turned out to be incorrect, it's actually negative, so that means it's compression. So I'm going to put this as compression. That's very important. So very quickly, I just want to show you what is the correct direction of forces at joint E? E, B turned out to be tension, so the direction of tension is away from the joint. And DE or ED turned out to be compression, so the correct direction is into the joint. There you go. So before I forget, I'm just going to take EB as tension on E, and I want to put the correct direction of the force at B. So I know BE is tension. What is the direction of tension on B? How do you do that? Well, now consider B. Put your finger on B and observe what is the tension direction like. Tension is pulling away from B. So this is the direction of the tension force on B. So look at this. The force on joint E is pulling away from E, and the force in the opposite direction is actually equal and opposite. It's pulling away from B as well. There is tension everywhere. There is tension on E from this end, and there's tension on B from the other end. Same thing with the force DE or ED. The force here is compression because DE turned out to be compression. So it's causing compression on E, and it's causing compression on D as well. So this is the correct direction of the force. This force is 4 kilonewton compression. You don't have to note it on the diagram. I normally will just look here, but for your calculations you can just note it as well. All right, so we know BE, we know DE, we also know DC. So that leaves us with 3 more joints to go.